Assalamualaikum warahmatullahi wabarakatuh. I be to Dr. Nurul Fadila. My name is Muhammad Aikhal bin Azmi and I will present to you my research project this year. The title of my project is Quantification of Carbon Dioxide Sequestration by Duckweed, Promoting Circular Economy in Tilapia Aquaculture. Increasing demand for marine and fish product has made aquaculture activities more prominent. Tilapia is one of the most common fish farmed because of its nature that can produce a high yield. Despite this, greenhouse gases such as carbon dioxide emission by the pond is something that needs to be assessed to reduce climate change effects. There are various research that study the capability of fast-growing microphage, such as duckweed, to sequester carbon dioxide. Though there is no paper that study carbon dioxide sequestration by duckweed used to treat tilapia pond effluent specifically. So, the objective of this study is to quantify carbon dioxide sequestration by duckweed in tilapia pond effluent, also in nutrient-added water. Next, we will move to the method used in the experiment. To quantify the carbon dioxide sequestration by duckweed, a static chamber method was used. This method has been used by previous studies to quantify carbon dioxide sequestration by duckweed used to treat different types of wastewater. The static chamber consists of cylindrical body with a dome-shaped top that are made of transparent material, which is acrylic. The carbon dioxide sensor used are the simpler one, where the reading need to be taken manually. Next, two types of duckweed culture medium was used, which is the tilapia effluent collected from a fish farm near Alor Gajah, Melaka. The other medium is the nutrient-added water that was made by mixing 30 liter tap water and 5 ml nutrient solution. Anti-chlorine solution was also added to remove chlorine from the tap water. The full setup will consist of a 55 liter basin and a lid with a hole in the middle that can hold the static chamber in place. A light connected to a timer was also added to make sure that the luminosity is constant throughout the experiment. The timer will allow to set the time for the dark and light period. Lastly, duckweed species used are the Lemna minor that was collected in a white point near Alor Gajah, Melaka. After the setup was finished, it was allowed to sit overnight to allow the carbon dioxide to reach equilibrium state. Then, the initial carbon dioxide reading was taken at 7 AM, as well as the top view picture of the duckweed inside the chamber. The data was collected for another 4 days at the same time. The result of the experiment was shown in the table for both nutrient-added water and tilapia pond effluent. Some adjustment was made before the experiment started because the carbon dioxide sensor was calibrated to ambient carbon dioxide concentration. This means that the sensor can only read carbon dioxide concentration of 400 ppm and above. To compensate this, carbon dioxide was blown by exhaling into the chamber through a tube. This will increase the initial carbon dioxide concentration to 2,379 ppm for the nutrient-added water. But for the tilapia pond effluent, the organic content and microorganisms inside the effluent produce enough carbon dioxide via decomposition. There is no extra carbon dioxide was added inside the chamber when the tilapia effluent was used. On the first day, both experiments shows the same trend where the carbon dioxide level dropped drastically. The reason of the drastic change is due to the high difference of carbon dioxide concentration inside the chamber and the culture medium, causing the more carbon dioxide dissolve into the medium. Previous study also proved that higher concentration of carbon dioxide can also lead to higher duckweed growth rate. This means more carbon dioxide will be sequestered when carbon dioxide concentration in the chamber is high. Looking at the graph of carbon dioxide sequestration rate per area of duckweed, the sequestration rate decreased throughout the experiment. Since the experiment was done in a small scale, nutrient depletion may affect the growth of the duckweed, thus reducing the carbon dioxide sequestration rate. Though, the same reason cannot be applied when tilapia pond effluent was used, as it has high amount of nutrient. As stated before, the tilapia effluent can produce carbon dioxide, where this affects the calculation of the sequestration rate. We can also observe that the growth rate of the duckweed when the tilapia pond effluent was used was higher than the nutrient-added water. The sequestration rate for the nutrient-added water ranged from 0.064 to 0.814 milligram carbon dioxide per centimeter squared per day, while when tilapia effluent was used, the sequestration rate ranged between negative 0.019 to 2568. In conclusion, the result of this experiment suggests that the duckweed culture effectively sequestered carbon dioxide from the atmosphere. The observed decrease in carbon dioxide concentration and the increase of biomass support the potential of duckweed as a tool for carbon sequestration. But it is worth noting that the current study that was done using tilapia pond effluent did not measure the exact carbon dioxide sequestration by the duckweed. These are a few recommendations that can be done. Further studies with improved methodologies and comprehensive measurement can be done. It also can be applicable in a larger scale environmental management strategies to obtain more realistic results. The experiment can also be done with added chamber that does not include duckweed inside the chamber to measure the amount of carbon dioxide released by the tilapia pond to measure exact sequestration rate. I would like to thank and express my appreciation to my supervisors, Dr. Luqman Hakim Baharuddin and Mr. Rajesh Azul Shah, for providing equipment for the experimental work and guiding throughout the project. I also want to express my gratitude to School of Chemical Engineering, UITM, for providing me with resources to finish the research project. Thank you very much.